No problem.
We can arrange it.
Okay, now we're live. 1 second. It's just because the live one has to be delayed. Oh, Matthias is there. Sorry, Matthias is like holding up his hand. He always tries to go into the different place. Oh, where's the streaming? It's supposed to be there. Okay. Now I'm here.
We can arrange it.
Okay, good. Sorry, over here. Excellent. Let me share my screen first, and then welcome everybody back. I see that we haven't lost so many. That's good. All right. So welcome everybody back to the 2023 New Year's resolution. We all attended online seminars from SPICE and SPIN+X seminars that we still continue. I know that there's a lot of overlap with other live seminars that we have now as well, but please keep in mind that all these talks are always online immediately after. And just as many of you are doing, you can watch it afterwards or whenever your schedule fits the best. But here, this is also made to reach a larger, broader society community for the very important scientists breakthroughs that are happening at the moment. As usual, this is a seminar organized in SPICE by myself, and in help with some young talent like Mechiel and Angela Wittmann, as well as a continued collaboration with Karen Everso-Sitter now in Duisburg, and in collaboration with the Collaborative Research Center SPIN+X that is led by Martina Schliemann in Kaiserslautern, now Rheinland-Pfalz Technical University, and Burkhard Hillebrands and Matthias Chloe, who leads SPIN+X here in Mainz. As you know, this is a webinar, so please write down your question on the Q&A or raise your hands, and I will give you the floor after the speaker finishes, or in between if it's necessary as an important question, so to clarify things. So it's my pleasure to start 2003 with a very prominent person. I had the pleasure to already invite him a while ago in James as a keynote speaker before, and now he's the director, Macron director of the MPI for multidisciplinary sciences now, and he graduated from Berlin University. Claus' team is well known. He explores new experimental methods, particularly in the time domain and the optical time domain, and has been the pioneer of this ultrafast transmission electron microscopy and ultrafast low energy electron diffraction, and has many awards, of course. Walter Scotty Prize Award, Principal Science Award, and long list in there that you can read afterwards. But I don't want to pass up most of your time. Let me just give you the floor, Claus, and please go ahead whenever you have a chance and start your talk.
Okay, thank you very much for the kind introduction and the invitation. It's a great pleasure for me to talk here. Let me just share my screen. Yes. Do you see the right screen? Okay. So, well, thank you very much for the introduction again. I would like to talk a little bit about recent developments in ultra-fast electron microscopy. So it's one of the key experimental techniques we use and develop in my group. And give a bit of an overview and then zoom in on electron light interactions and their application and study in electron microscopy, actually. So just a little bit of an overall background, why we initially went into this area of ultra-fast electron microscopy. And it basically stems from some of the ultimate challenges, you might say, that we have in the study of solids and nanostructures, which arise from the strong interaction and correlation between the different degrees of freedom that we have in matter. So let's say we start with a single crystal, basically a simple layered material, something like that. It's easy to plot, but very difficult to understand, in particular because the particular states, complex correlated states of matter, arise from the interaction of, let's say, spin, charge, lattice degrees of freedom in particular. So It would be great if we could add new experimental tools to learn more on the emergence and control of correlated states of matter, such as charge density wave states, superconductivity, for example. Then, in addition, the let's say energy problem and sustainable energies, of course, long-standing societal challenge, and understanding of energy transfer processes and redistribution between these different degrees of freedom is really essential to understand, control, and make more efficient, for example, light to electricity energy conversion. So basically, if you want to both understand the interplay of these different degrees of freedom and then harness them in future applications, we need to talk or act on a system with external forces and excitations, such as optical excitation, electricity, magnetic excitation. Yeah. In particular, a lot of materials can also change their physical properties in applications by carrying out particular pathways from one state to the other, not just magnetic materials, but also materials exhibiting structural phase transformations. And also in those, essentially the interplay of different degrees of freedom play an essential role. And so in order to really understand these microscopic couplings, one has to go not only to a high spatial resolution, but also to high temporal resolution, because the fundamental interactions play out on short time scales, as many of the previous talks in the seminar series have elucidated, from, let's say, nanosecond, picosecond timescales down to femtosecond, attosecond timescales, in a hierarchy of couplings and correlations, essentially. That's essentially this larger research area and research question has concerned us over many years. And our experimental approach to the problem has been to try to achieve simultaneously high spatial and temporal resolution by the development of ultra-fast transmission electron microscopy. So what an ultra-fast transmission electron microscope essentially is to take the spatial resolution, the high spatial imaging resolution and diffraction resolution of an electron microscope and try to combine that with the temporal resolution of ultra-fast optical spectroscopy. So it's an optical pump electron probe technique where you start with a regular electron microscope with an electron source at the top and transmitting electrons through a sample, but now not in a continuous way, but basically in a pulsed way, such that the electron beam is basically pulsed. You produce flashes of electrons, which then allow you to take snapshots of the dynamical evolution of a sample, where the evolution is induced and triggered by an optical excitation pump pulse. So it's an optical pump electron probe technique, which essentially takes the temporal resolution from the laser side and the spatial resolution from the imaging capabilities of the electron microscope. And one of our primary areas of emphasis in the development in the last years has been to really work on the photoelectron cathode, which produces the pulses of electrons, and to make sure that we get best temporal resolution and best spatial resolution from these electron pulses. And our approach has mostly been focusing on nanotip cathodes, basically, so sharp needle cathodes, where the electrons are essentially emitted from the very apex of these tips, because this ensures both high spatial coherence of the electron beam, which allows you to get good diffraction and spatial resolution, and also short pulse durations, because the electrons are really accelerated up to fast velocities in the very close vicinity of the tip. Okay, so let's take a quick look at into the lab. This is our Ultrafast TEM. It's basically a initially commercial electron microscope, which we've modified to allow access in two ways, as sketched on the previous slide. Basically, the probe pulse producing the electron pulses is coupled into the electron microscope to produce the electron pulses. We can get induced emission basically from the very front facet of one of these zirconium oxide coated tungsten field emitters, such that we have a very nice localized source. And we have another beam, which is basically the pump beam going into the sample to excite and induce structural or magnetic dynamics in the material. Okay, so here are some typical specifications that can be achieved in this microscope. The electron pulse duration down to 200 or slightly shorter pulse duration approximately, and then you can focus this electron beam as a regular electron microscope beam, essentially down to sub-nanometer dimensions. And you also have decent kinetic energy resolution. So essentially, what this constitutes is then a nanoscale local probe of structure and electronic excitations, as far as that's possible, also in the electron microscope, with sub-nanometer spatial and sub-picosecond, few hundred femtosecond temporal resolution. Okay. Yes, the microscopic emission mechanism, I should just mention quickly, is linear photoemission over the barrier of this Schottky field emitter. So you basically heat this tip to moderate temperature above 1000 Kelvin. So you have a slight Fermi tail in the electron distribution here, and you use a photoelectron or photon energy such that electrons are emitted slightly over this Schottky barrier produced by applying a sharp or strong static field to this tip. It's important to note that this is a linear photoemission process because essentially in this way you can use an arbitrary structuring of the electron pulses. So you can use femtosecond pulses, picosecond or nanosecond pulses, depending on the desired temporal resolution for the particular experiment, or even continuous wave excitation of the source. Okay, so now there's a range of applications of this ultrafast microscope, and I don't really want to go into detail with too many different applications, but basically just essentially describe one. But here's just on this slide, a bit of an overview. You can use now this beam, focus it onto a sample, and then record diffraction images, basically, in the far field behind the sample. So by conical illumination, for example, you have a range of incidence angles, and the Bragg condition, so the diffraction condition from a crystalline material, then develops into essentially diffraction lines. And indexing each of these lines basically allows you to reconstruct in a three-dimensional manner the size, orientation of the unit cell, such that you can do basically local crystallography in something called convergent beam electron diffraction, as is conventionally used also in electron microscopy. And now the nice aspect of this with time resolution is that you can study the local structural evolution after optical excitation. So basically following these different lines, which correspond to different Bragg conditions in diffraction, allows you to study as a function of time and space. If you scan the beam, then the local distortions of the unit cell, rotations, deformations, also volume changes, basically. So here, for example, it's just as a function of the optical pump, electron probe delay, the evolution of line positions and line shapes, which can then be used, as I said, to reconstruct the unit cell, and the strain evolution, the propagation evolution of strain waves throughout the material. Okay, another very different example, which also works with the same optical excitation of the tip, the same production of electron pulses, but a different sample excitation is shown down here, because we can not only use electron or optical excitation of the sample, but we can also drive currents through a sample in a way that is synchronized to the electron beam. And in this way, basically, so if you can see this here, you have laser pulses on the tip, and here we've synchronized a radio frequency current passing through a permalloy thin disk. Here, synchronized it in a way to record a stroboscopic image of the magnetization dynamics driven by this radio frequency current. So it's this gyrotropic oscillation in this particular case of a vortex core in this permalloy thin film driven at a resonance. And as you can see, basically also here with picosecond resolution, record this magnetization dynamics. The imaging condition here is actually a defocused phase contrast imaging, so you can get access in an electron microscope to the magnetization by slightly defocusing the image and using the deflection of the electron beam due to the Lorentz force in order to get contrast of the domain walls and the vortex core, which show up here as bright lines in this otherwise relatively homogeneous contrast. So if you're interested in more detail in these, I can talk about that in the question section, or check out these references here. Okay, third example, stop this here, is the study of phase transitions. So we can also, by diffraction contrast, basically access structural phase transitions in materials. So metal insulator transitions, for example, coupled to a lattice distortion, and with proper contrast, as I'll show on the next slide, to also study these types of transitions. Okay, so let me jump into this example a little bit more. It's about the ultra-fast imaging of a structural phase transition coupled to a metal insulator transition in a material. So this is a 2D van der Waals material, tantalum disulfide, which is composed of tri-layer stacks of tantalum atoms sandwiched between sulfur planes and then stacked on top of each other. Basically, if you look on top of the tantalum atoms, they're given this kind of hexagonal regular lattice here. But if you cool this material down to below a critical temperature, there's a transition from the high temperature metallic state to the low temperature insulating state. So it's a spontaneous breaking of translational symmetry in this material, which basically couples charge localization, so transition from metal to an insulator, with a periodic lattice distortion in a way that the atoms contract basically in a hexagram shaped towards central atoms, basically forming a superstructure in this material. Yes, it's a very prominent charge density wave transition coupled to a periodic lattice distortion. In this transition, the electric conductivity changes by many orders of magnitude, actually. So how does this show up in the electron microscope? If we transmit a parallel electron beam through this material, we see this diffraction pattern with a 6-fold symmetry, basically composed of bright and dark diffraction peaks, where the bright diffraction peaks correspond to diffraction from the host lattice. So essentially, those are also present in the undistorted metallic state. And the superstructure formed by the long-range periodic lattice distortion leads to these subtle, much weaker superstructure diffraction peaks in between the main lattice peaks. Yeah? So the actual size of the unit cell, of course, in this superstructure crystal is larger, which means this leads to smaller diffraction angles, essentially. And because it's only a subtle change in the lattice constant, so exaggerated here, but in reality only a few percent of the bond spacing is changed. These are about 2 orders of magnitude weaker than the main diffraction peaks. Okay, so yes, hexagonal lattice, periodic lattice distortion. So if we now want to study the transition of this material from this low temperature insulating phase to the high temperature metallic phase by optical excitation, what we need to do is again do an optical pump and then electron probe beam and then record these diffraction patterns as a function of delay. Here's some exemplary data. Basically, this is the normalized intensity, normalized to before the optical excitation intensity of these superstructure diffraction peaks for different fluences. I don't want to go into too much detail here. Essentially, what you see is a very fast quench of the structure, so a transition towards this phase within the first picosecond, and then depending on the fluence, when you're above threshold, basically you completely quench this structure. At intermediate fluences, there's a partial suppression and then a relaxation back towards the initial structure. And from these time constants, basically, you can study the type of coupling, the types of states that are initially excited and how strongly they couple to this lattice distortion and how rapidly they can relax. Yeah? But ultrafast diffraction, we just record the intensity of diffraction peaks, is not exactly the ultimate strength or the ultimate focus of the electron microscope, because really what we want to access is also spatial resolution. So we want to see how does this transition actually occur in real space. Yeah? So to that end, what we need to develop is essentially access to the spatial distribution of these different phases in the material. Yeah? And so here we actually developed a trick for this paper that allows us to emphasize and focus only on those diffraction peaks which are associated with the lattice distortion. So as I mentioned earlier, we have the diffraction pattern, which we can record in the electron microscope, composed of strong and weak beams. Now, unfortunately, as I said, 90-some% of the diffraction intensity is composed in these peaks, which don't tell you too much about this lattice distorted phase. So what we can do is essentially place in the back focal plane, so in the far field basically of this diffraction pattern, a tailored dark field mask which blocks all of these bright diffraction peaks and only transmits the peaks corresponding to the superstructure, so arising basically from diffraction from the lattice distortion. So when we place this mask in the back focal plane of the objective lens in the microscope, and then use the imaging capabilities of the electron microscope to come back to a real space image, then essentially we have an analog filtered, Fourier filtered image, which gives us information about the spatial distribution and the of the lattice distortion. And the intensity of this image is going to be directly proportional to essentially the square of the amplitude of the lattice distortion. So wherever intensity passes this mask, there's large lattice distortion. Wherever little intensity passes through this mask, there's little lattice distortion. Okay, so this is now taking two real space images, one without the mask inserted, one with the mask inserted, of about a 1 micron sample here. This doesn't look too exciting at first, but you need to realize that the lower image is basically a direct measure of the lattice distortion and, in essence, of the order parameter of this phase transformation. So it's kind of a new way here to get access to structural order parameters of phase transitions. Okay, so let's just take a look at the sample before I show the time resolved experiments on this. So we have this here, a 70 nanometer flake of this material. And in order to ensure that we don't have too much average heating of the sample when we optically excite it, it's actually placed underneath a near spherical mask composed of gold on silicon nitride, such that when the laser excitation comes here from the top, only a very small region is excited, and the rest of the optical intensity is basically blocked. We only excite a small portion here, and we have very good thermal contact of this excited material, which allows us to do this experiment at quite high optical repetition rates without heating up the material in the process. Yeah. Okay, so this is a scanning transmission electron microscope image. Transmission electron microscope image is just different ways of imaging the sample, either with a scanned focus beam or with a parallel beam. And essentially what you take from these images is that it's a relatively homogeneous sample. You have a little bit of a flaky nature of this 2D material, but it's actually, in fact, quite homogeneous. There's one point we need to consider now with the optical excitation, as the pump pulse is going to be impinging on the structure here. There's going to be some diffraction from the side edges of this mask over here, which is going to shape the optical excitation profile and the regions where the sample is going to be particularly prominently excited. Okay, so let's go to the time resolved experiment here. This is now again with this mask inserted. So this is before the optical excitation at negative delay times. The image intensity, the dark field image intensity. So it's a measure of the strength of the lattice distortion as a function of space in this material. This is the optical excitation profile, which we determine from reference measurements, essentially, such that the optical excitation incident here leads to scattering from the sides and leads to basically optical hotspots in this excitation here. And now we vary the delay. So take a movie of the evolution of this periodic lattice distortion as a function of time and space, and obtain these snapshots here. Yeah. There's a number of things we can extract from these. One of the things you might immediately see is that there's a relatively global suppression of the intensity at very early times and somewhat gradual transitions of the intensity over here. Whereas at later times, one actually has relatively well-defined phase boundaries between these phases. So what this corresponds to is essentially the initial optical excitation suppresses the charge density wave and the periodic lattice distortion almost everywhere in the material, as in the diffraction data I showed a slide earlier. But then, depending on the strength, the local strength of the excitation, you're either above the threshold or below the threshold, such that there's a back relaxation in regions which are weaker excited, and above threshold excitation. So actually switching of this phase transformation in these hotspots here, and you get a phase separation essentially between those two regions. And already at about 2 picoseconds, you already start to have these phase boundaries formed, essentially. So what we can extract from this, if you want to take a closer look at this data here, we see is essentially formation of phase boundaries and then slow relaxation back to the original phase over timescales of several hundred picoseconds. Okay, so that was basically the example I wanted to show on structural dynamics probed in this ultrafast TEM, but there's a completely different area also that we can access in these microscopes by having optical excitation on the sample, and that goes a little bit away from the traditional use of an electron microscope and doing this with high temporal resolution, but it really goes into a fundamental area of, you might call this quantum probing in electron microscopy. The point here is that you can view the electron microscope combined or composed of an electron source, a beam-forming system, interaction with a specimen, and then an imaging system, and really define it or redefine it in a way as an optical bench for the study of the interaction of electrons with light, yeah, or samples, basically, yeah, such that basically in the top here, by using this laser excitation, we can produce well-defined electron states. We can use the condenser system to manipulate the state in a particular desired way, and then study interaction with samples. And then, you know, behind the sample, you can do some post-selection and so on and so forth. And there's been quite a number of works in our group and other groups in the community to really look at electron microscopy from this different perspective. Yeah. So the goal in this year, and this is basically for the remainder of the talk, is to develop strategies to prepare, manipulate, and create or characterize specific quantum states of the electrons, and in this way develop a quantum optics framework for electron microscopy, with the goal, for example, to well, access different observables and to really you know, create different opportunities for electron microscopy, let's say. Okay, so we can basically go to different positions in this flow, from preparing the states to manipulating and so on. And I want to give a few examples, starting with the state generation, because you might think that it's pretty straightforward. Actually, you take the tip at the electron source, you shoot at it with a laser, And then that's it, right? So you produce electrons in a kind of a stochastic way, but there's actually, as we've very recently discovered and posted on the archive just a couple of weeks ago, as quite some interesting stuff happening at this source. Yeah. So what we can do is basically use a new type of electron detector, which allows us to record the kinetic energy distribution of the electrons emitted within each laser pulse. So basically, we have an electron spectrometer. Say right now, we just take out a sample, we just shoot the laser at the tip, and we record the electron spectrum. Here, we have a sequence of laser pulse. Of course, it's a mode-locked laser, one pulse every nanosecond, or one. We actually use this at somewhat lower repetition rate. So say one pulse every 10 nanoseconds or so. And then the temporal resolution of this electron detector here that we use is high enough to count the number of electrons in every laser pulse and also measure the electron energy of every electron in each laser pulse. So for example, here as a function of laser power, said it's a linear emission process. This is the rate of laser pulse events which have led to the production of a single electron in a laser pulse. So these are basically one electron events, and they linearly increase basically. So this goes in this laser power range here from let's say every 100 or so laser pulse, 100 would be every 100 would be here, a laser pulse producing one electron, up to every 10th laser pulse producing one electron. Okay. Now, in the same set of measurements, occasionally 2 electrons will be produced, and the probability of that is approximately the square of the probability of producing 1 electron. Yeah, so here what we have is basically the rate of 2 electron events, and also we can produce 3 electrons being transmitted through this whole microscope column, basically. And these scale approximately with the cube of the probability. So more or less as expected from Poissonian statistics, random statistics, you have a chance for 1, you have a chance for 2, and you have a chance for 3. And that more or less works in an uncorrelated statistical way. There's a little bit of an anti-bunching, a little bit of a weakly sub-Poissonian statistics, and microscopic origins of this might be different. Could be Pauli exclusion, basically from electrons emitted from the same state. Could also be Coulomb repulsion. That's not our main focus here, but I could talk about that if you have a question. What's more interesting at this point is actually that the spectral distribution of these different events, the 1 electron, the 2 electron, or the 3 electron events, are really drastically different. Yeah. So now, as I said, we're in a condition where the average electron production rate for these conditions is a little bit less than 1. So the event average spectrum more or less looks like this. This is the energy distribution of the electrons, and we subtract the acceleration voltage of 200 kilo electron volts in this case. Okay, now if we only look at the electron states which contain, or the events which contain 1 electron, this is a single lobed, slightly asymmetric spectrum, not so interesting, basically, as expected. But if you only plot the electron energy distribution of the 2 electron events, there's a drastic change in the spectrum, and the spectrum develops into a 2-lobed structure. Yeah, so which already might tell you that there's actually an interaction of these 2 electrons. You can't emit 2 electrons at nearly the same energy; they're actually repelling each other. But the interesting question is actually, why are they repelling each other to such high energies? Because this would indicate that the electrons are actually emitted from a very, very small volume, much smaller actually than what we would have expected from the size of the source. And then thirdly, if we only plot the electron spectra that arise from the 3 electron events, so those laser pulses which have produced 3 electrons, you get a very well-defined 3-lobed structure here, which is also not exactly expected from the source, because it's actually a larger source than what you would guess from having such strong interactions. Okay, but let's look a little bit closer at the distribution of these electron energies. So as I said, we can record the electron energy for each of the laser pulse and for each of the electrons in each laser pulse. So if you only look at the 2 electron events, what you have here is now you can plot the distribution of events as a function of the energy of one of the electrons versus the energy of the other electron. Yeah? So you have here like a 2-dimensional correlation plot. And what you see is quite a strong correlation gap, such that you don't find electrons at the same energy. One of the electrons is always in this lobe here, the other electron is always in this lobe. Yeah? So there's a strong anti-correlation in energy, no electrons found at the same energy. This is a clear evidence, clear proof, basically, of the strong Coulomb interaction of these two electrons. If we just plot this now as a function of the difference energy, this is the correlation function, energy correlation function for different laser powers. It's weakly dependent on laser power only. And this shows that there's actually an energy correlation gap of more than 1 electron volt, which means that it's not possible to emit 2 electrons from this source with an energy within the laser pulse duration, about 150 femtoseconds. Or it's not possible to emit 2 electrons within these 150 femtoseconds with an energy difference of less than 1 electron volt. And that's actually quite surprising. It does not correspond, I should be honest, to the simulations, numerical simulations, which we've carried out. So this really suggests that there's a new type of 2-electron emission process, which has not been reported before, 2-photon, 2-electron emission process, which directly leads to a strongly Coulomb correlated 2, and in this other case, also 3 electron states. So I hope maybe Martin Eschlimann is listening. I'm looking forward to your question on this, because it's really quite a puzzle, not expected, and there's couple of details, nitty-gritty details in this problem, which are very hard to reconcile with with some of the assumed or known parameters of such sources. Okay. Now, what is this good for? First of all, I think it could be interesting and important for just fundamental considerations of photo emission processes, I think. But also there might be an application of this because, as I said, we have more or less a random distribution of the rates of these events. But at the same time, the energy is very strongly correlated. And what this means is that this energy distribution actually allows us to exert statistical control over the number distribution of these electrons. So what this means is essentially, for example, we could place an energy dispersing element in the beam path and then select only electrons which are more or less residing at near this mean energy. And in this case, you could basically strongly suppress the 2 electron events because 1 electron has higher, 1 electron has lower energy, and only the 1 electron events can pass. What this would do is essentially produce sub-Poissonian distribution, so eliminate short noise basically from the electron emission process, which could be useful for a number of applications in imaging and lithography, for example. Okay, let's, for the remainder, go down this column a little bit and look at state manipulation and interaction of electrons with optical excitation in the material. So just very brief background introduction to this problem. It's of course very well known, has been studied for decades, that electrons can interact with optical near-field and near-fields and optical excitations in materials and nanostructures, essentially by harnessing the fact that an electron can be viewed as a time-dependent dipole, or has a time-dependent dipole moment with respect to the sample plane. Yeah, so passing by a swift electron by a material can induce an optical polarization, which can either decay or can re-radiate, yeah, in the form of cathodoluminescence. Yeah? Both processes, so non-radiative and radiative decay of this polarization, will lead to electron energy loss. which can be spectroscopically probed, such that passing electrons near a structure or through a structure is going to produce a characteristic for a given material and a nanostructure loss spectrum. So the distribution of electron energy loss events relative to the incident energy is going to give you a lot of information about the optical excitations, for example, in the material. You can use this essentially now scanning the beam or having a parallel beam and then energy filtering. And if you basically look at different loss energies with respect to the incident energy, for example, here we characterize the plasmonic modes on one of these conical tips, basically producing standing wave patterns of plasmons propagating towards and away from the apex. Also for these nanotriangles, for example, you can get characteristic scattering probabilities, so loss distributions at different energies, and they directly represent the optical modes, plasmonic modes of these such structures. Now, what we can do in the Ultrafast TEM is not only look at the emitted cathodoluminescence or the spontaneous loss distribution, but we can also use the optical excitation to populate a particular mode and then study the scattering probability. Yeah. So essentially the description for this is relatively straightforward. It's essentially just computing the probability that an electron gains or loses energy by interacting with the time-dependent field projected onto the electron trajectory. Yeah. So what's relevant both for electron energy loss and for this process is essentially the scalar product of the electron velocity with either the self-induced field, so the field produced by the electron itself acting back on the electron, or by the external field. Yeah. When you Fourier transform it, basically you get the electron energy loss spectrum or this photon-induced near-field electron microscopy spectrum. So if you don't just look at the spontaneous loss, at the stimulated loss, you can not only have spontaneous scattering to lower energies, but also get electron energy gain by electrons picking up energy from the electrons, the electrons, sorry, picking up energy from the light field. Yeah, this was first done in at Caltech in the group of Ahmed Zuhail. They call it photon-induced near-field electron microscopy, because this is a way essentially to look for an electron microscope beam to look at the strength of optical near fields by essentially populating not just one of these photon orders that you produce but by multiple ones. So the electron energy spectrum of passing electrons through this near field is then composed of multiple sidebands, which corresponds to the absorption and the emission of one or multiple photons. Okay, and now what you can do is, besides just this electron energy loss spectroscopy, also look at other processes which correspond to the stimulated version of this process. In this way, you are probing specific modes that you excite, so you can change the optical polarization and then really look at the specific mode profile or the wavelength and tracking out particular resonances very specifically and for a given optical excitation, basically. Okay. Let me actually jump a little bit here to, to the most recent work on this. So besides basically being used for as a means to characterize optical near fields and whatever plasmatic modes and nanostructures and so on, we're now also looking in more detail into the fundamental scattering process that this involves, and also using this as a means to actually couple an electron beam to optical cavities. Yeah, because essentially what we would like to do is to go a little bit in this direction of quantum optics with free electrons. So using an electron beam, for example, to read out the quantum state of an investigated individual quantum system, of a quantum dot, for example. And the first step towards this direction is actually to make sure that you enhance the coupling to a particular optical mode to as large as it can possibly be. Yeah. And one way to actually enhance this coupling is to study phase-matched interactions of electrons and optical modes. Yeah, so what we've looked at are these whispering gallery mode resonators. They are dielectric spheres, very well known from, I guess, cavity quantum electrodynamics studies. They actually have the nice property that besides enhancing the optical field within these modes, you can actually make sure that there's phase matching in the interaction of the electrons with these optical modes as soon as the electron group velocity coincides with the optical mode's phase velocity. When that's the case, the electrons can basically interact with the same phase of the optical field for prolonged times and really produce quite strong interaction and really populate multiple of these sideband modes. Yeah, most recently, we've actually gone even one step further to make sure that the electrons actually can strongly couple to just a single mode of the optical field. And to this end, we've teamed up with the Kippenberg group at EPFL to fabricate specifically designed optical resonators, which allow for phase matching of this interaction, electrons to the cavity modes, which have well-defined optical near field going into vacuum. So they have a vacuum interface where we can pass the electron beams through, and where the quality factor of these resonators is substantially higher than for the other structures that we had studied before. So in this case, approaching 10 to the 6, which means that even weak optical excitation, so continuous wave excitation, actually leads to sufficiently strong coupling to affect the electrons here. Yeah. So what this means is by you have a quality factor of 10 to the 6, you couple in only 1 milliwatt, so a small laser pointer power essentially into this waveguides. Then within these cavities here, you transfer this into 1 kilowatt. And this 1 kilowatt is actually sufficiently high field strength to very strongly affect the electron energy spectrum and modulate in energy the electron beam. Yeah. So here's an optical microscope image of these structures. So this is the waveguide. This couples into this high quality ring resonator, and you pass the electron beam through the optical near field and then again measure the kinetic energy spectrum. Yeah. And the coupling here is actually so strong that all of these experiments do no longer require the ultra-fast, let's say femtosecond laser excitation, but can be done with low power continuous wave beams, and also can be done in the conventional continuous electron beam. So either using continuous wave laser excitation of the tip or using the standard continuous electron beam. So we can populate multiple of these orders, actually going to hundreds of photon exchanges, which means that a single electron either absorbs or emits hundreds of photons. So it's a highly nonlinear process in the electron-light interaction here. Okay, we've also characterized this actual phase matching. So the electron velocity, of course, changes with changing the electron energy. And there's a peak as expected, so simulated and experimentally measured a little bit in this vicinity of 100 kilo electron volts. Okay, we can now scan the electron beam at different energies and actually map out these mode profiles here. You see, as you scan the electron beam across the circumference of these structures, you actually see sort of an oscillatory pattern, which is just sort of a phase mismatch by interacting with two different locations of the structure. You can do this as a function of energy and then fully characterize this optical field. And again, this is an intracavity optical field exclusively probed with an electron beam at very high spatial resolution. Okay, so final few slides, I'd like to go even a little bit further into this direction of looking at individual scattering processes and also studying eventually entanglement of this optical cavity with the electron beam. And so to this end, we actually switch off the optical excitation of the resonator. So we have an empty resonator, and we just pass the electron beam through the optical near field, or through the vacuum near field, if you wish, of this resonator, producing a cathodoluminescence, so spontaneous generation of radiation into this cavity mode. Okay, this is what's done here. So it's an empty resonator. We pass the electron by, and we record photons generated. This is the optical spectrum that we can measure with an optical spectrometer at the output here. If we do this with a little bit better spectral resolution in the spectrometer, we actually see that what we produce here by a single electron, or by a large ensemble of single electrons, is the longitudinal cavity modes of a particular mode family, the mode family which couples to, or which corresponds to this longitudinal field, which is phase mesh. Yeah? So we have individual resonances here, optical resonances that we populate, and the spacing corresponds to the free spectral range of this resonator. Okay, it's limited on both sides by the detector efficiency and also by the phase matching condition. Now, what's kind of interesting is what we can do here is not just measure the cathodoluminescence, but we also have the electrons which have passed by. And in the electron spectrometer, which is basically a magnetic sector spectrometer, they're deflected, and we can measure the kinetic energy distribution of each individual electron. Yeah, so this now allows, with a particular electron detector, which has sort of single pulse timing resolution, pretty much, and also allows for an additional signal. We can now do coincidence measurements, basically, between the electrons impinging on the detector after the electron spectrometer, so resolved in terms of energy, coincident with photons produced and recorded coupling out of this resonator. Yeah. So what this now allows us to do is basically to do these coincidence measurements and measure the distribution of events, of electron events, the energy of each electron event, and the time difference between an electron event and the next photon that this photon detector has measured. Yeah? So what we see here is basically a range of uncorrelated background electrons not having lost energy. So those are just electrons which have not scattered at the resonator, have not produced a photon. But at zero time delay, in this coincidence experiment, we see a strong peak of correlated events, which correspond to electrons having lost one photon energy and a photon detector having detected that very photon. Yeah. What this means is this is a correlation experiment, coincidence experiment of single electron producing a single photon, essentially. What we can now do is basically post-selection experiments and look only at those events where an electron has lost an energy. Then we know that this cavity has been populated with a photon. So essentially, this is a heralded single photon source, an electron heralded single photon source, and single photon cavity population. Yeah. We can now use this in terms of correlation imaging. So we have electron energy loss or energy loss distribution, scanning the electron beam in the vicinity of this resonator. We can also plot as a function of this scanning in this vicinity the number of photons collected, but now we can do this in coincidence and basically only look at those scattering events where really one photon has been produced in the cavity. And as a function of distance from this resonator, for example, this may be going into a little bit too much detail, but you can imagine that when you have two observables, the electron loss and the photons produced, you can actually suppress background signals and get higher dynamic range. And what we see here is basically that this coincidence imaging for electron microscopy allows us 2 orders of magnitude signal enhancement. Okay, last slide. What this process doesn't only allow us to do correlation imaging, but it also actually gives a bit of an insight into the possible entanglement of electrons and these cavity excitations. So when we basically can look at this in terms of the combined states of the electron system and the cavity system, we start off in a situation where electron has energy E0, the cavity is empty. After the interaction, we actually have an entangled state where the electron can have lost one or more photons or 0 photons. And this is coinciding basically with the production of the corresponding number of photons. And now in post-selection, so measuring the electron energy, what we produce is a particular pair state between the electron and the photon. Yeah, now we've done this for a single photon, but this can also be used for producing multiple photon Fock states, so 2 photons or 3 photons. Or when you manipulate the electron beam by other ways, you can also have more complicated photonic states, which are directly produced by a well-defined electronic state. Okay, so with this, I'd actually like to just acknowledge my collaborators in these different teams. Primarily, I've been talking about this Ultrafast TEM work, but we also do Ultrafast lead, other works, and I'd like to thank you for your attention.
Thank you very much. This is quite a potpourri of very different techniques. So now we are open for questions. Martin, would you like to go first? Yeah. Please raise your hands, you guys. And
I did not raise the hands, but of course I have a question.
And you would.
As mentioned by the 2 electron energy correlation, which is a little bit similar to the measurements from Kirchner, the coincidence spectroscopy technique. And discussed with him several times if we can distinguish how you create these 2 electrons, if that's a simultaneous excitation or if it's a sequential excitation. You create first a high energy electrons to a nonlinear effect, and later due to a scattering process, a second electron. Can you say something if you can distinguish between these 2 processes?
So I think, yes, very good question. So of course, I had forced you also to ask something, but I think one of the key distinguishing factors of these experiments to the Kirchner experiments were that they were looking at 1 photon, 2 electron production events. So they were basically going, above a threshold for basically 2 work functions. And in this case, for example, they studied something like a resonant Auger process where you excited 1 electron, and then this basically was excited 1 electron to significantly above the vacuum level, which could then scatter and produce basically 2 electrons at near threshold. So here the situation is a little bit different, because in the single photon 2 electron emission process, you know that those electrons should already be quite strongly correlated, right? Because from a single photon in a linear photon emission process, you wouldn't expect 2 electrons. Here, the situation is such that we look at very close to the threshold where a single photon can emit 1 electron. And these are the events where 2 photons have been used to emit 2 electrons. So there you wouldn't necessarily expect such a strong correlation. These electrons could be emitted in an uncorrelated fashion from the entire source of the emitter, which is a lot larger than a single nanometer, right? It's several tens of nanometers in principle, the source. The strange thing about our process is that it seems that all of the 2 electron events that are produced seem to be such that the electrons were emitted from a volume of about 1 to 2 nanometers in diameter. So I'm not sure if that answers your question, but this is basically the main puzzle. So we are not really exactly at the point where we can say now we are absorbing 2 photons and then by a single electron, which then couples to other electrons, or whether these are uncorrelated events. We cannot distinguish this. Yeah, but the only.
Do I understand you right? You consider 2 processes. You excite linearly 2 electrons or non-linear 2 electrons, but you cannot distinguish between these 2 effects. Is this correct?
I would say right now we cannot distinguish 2 electrons excited by 1 photon each, or 1 electron excited by 2 photons, which then scatters with another electron to also emit 2 electrons.
Okay.
Now, I think the fact that we have the strong energy correlation somehow suggests that these would not be just 2 uncorrelated processes of one electron absorbing one photon each. So this must be a single step process, basically.
Yeah.
Otherwise, these electrons would not be this strongly energy correlated. Yeah.
Perfect. Gisela, like to.
Thanks for this fascinating talk. I have possibly a very silly question. So if have you thought about, or is it possible or impossible to have a spin polarized tip or a gallium arsenide source with a circularly polarized laser to produce spin polarized electrons? So you would have, if it's possible, an additional degree of freedom.
No, that's not a silly question. It's a very good question. I just think that in the electron microscope is maybe not the ideal candidate to work with spin polarized electron sources, because the well, I don't know, spin dichroism or spin dependent interaction at these high energies is minute, is very small. So what this would make more sense at a low energy electron microscope in backscattering diffraction, for example, or for the lead, which we do in other experiments. So we're in the process of developing ultra-fast low energy electron microscope for backscattering diffraction. So for that, it might actually be quite useful. Yes.
Okay, thank you.
Thank you. Any further questions from the audience? If not, I have, in terms of the imaging that you do, when I noticed that, particularly in the magnetic imaging, it works pretty well at the ferromagnetic resonance scale. How far can you push to do this close to the terahertz scale of the antiferromagnetic systems?
In terms of, I think it's, I mean, the one of the challenges, of course, is the sample excitation. So if you want to have some resonator nearby, in principle, it shouldn't be a problem to produce, far field, either broadband terahertz excitation, or maybe couple this to a resonant structure in the vicinity of the sample to enhance particular frequencies. I guess one of the things one has to consider is that when you have very strong electromagnetic fields in the vicinity of the sample, they also will interact with the electron beam. So if you have strong terahertz fields, for example, this changes the electron kinetic energy spectrum. This might lead to deflections also. And so it might not be so straightforward to fully separate the magnetic contrast from the direct action of these fields on the electron beam. In particular, because this magnetic contrast is relatively subtle. So these are very small deflections, microradian type deflections, whereas the direct coupling to an electrical field and a strong electrical field might
but if you have a single crystal, and particularly I'm thinking of these new phases that we've seen of ultramagnetism, where you have antiferromagnetic, compensated orders and suddenly no fringing fields, but bands that have a strong time reversal broken, but anisotropic, would that be something that you would be sensitive to? So meaning that you can actually see, in the momentum space or in the response that you would see some spin polarized currents and spin responses similar to the ferromagnets, but without these fringing fields that could affect the beam. Is that something that you could explore? I think
in principle, yes. All a matter of signal strength. So if the spin polarized currents, we have tried to work on that a little bit, but of course, then the question is really how strong are the fields, right? So compared to this is all in saturation magnetization, basically. So that might be larger. I guess I didn't have time to talk about that, but we're also doing this high harmonic imaging with circularly polarized radiation, which is element sensitive. It's not affected by any stray fields or fringe fields. So I think that might be, and it's very, very sensitive. So that might be better suited.
Okay. Igor, go ahead and ask your question.
Thank you. My question about tantalum sulfur. Is it known what is the band gap there, and it is connected with sensitivity of the method? So if in this lower phase where you have insulator, you have gap.
Yes.
And you feel it somehow with electronic beam.
Yes, so I should have included a slide. Basically, there's a lot of ultrafast angle resolved photo emission spectroscopy on this, which basically studies the size of the gap, the quenching of the gap. So here, our technique is really only sensitive in terms of the electron beam, only sensitive to the lattice distortion, so to the crystalline structure. So it's very complementary to the ARPAS work. Yeah, and in particular, in terms of scattering cross section, basically, or structure factor. Primarily to the tantalum atoms. So we're not very sensitive to the sulfur displacements. So mostly what we see is in plane tantalum displacements. But of course, in principle, what you could do with this experiment is also vary the wavelength. So what this experiment is done at a photon energy where we excite quite high above the band gap. So I think the gap is maybe, I don't want to say anything wrong, but it's on the order of 100 MeV or something like this here. Yeah, I'll have to check. I can give you the numbers. So there's ARPAS work by Kai Rossnagel, Michael Bauer. I guess Martin is also was part of that first work on this.
Mm-hmm.
Yes.
Okay. Thank you. Thank you.
Excellent. Well, I think with this, is anybody further questions? I want to thank there was 100 today in the audience together with the other the one online. So I think I'm happy to see that people are coming that are coming back and still